Once upon a time there was a milk barn where we used to milk a cow or two. Remember how we worked away the hours, dreaming of fun things we'd rather do. Those were long days, my friend, we thought they'd never end. We'd plow and toil forever and a day. It's not the life we choose, we work and never snooze, for we were poor and hungry every day. La 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 la, la 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 la, la 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 la, la 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 la. Then the hungry world came calling to us. We had to get productive right away. We could not sit by and watch them languish. Our science and genetics saved the day. Those were long days, my friend, we thought they'd never end. We'd plow and toil forever and a day. It's not the life we choose, we work and never snooze. Those were hard days, oh yes, those were hard days. La 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 la, la 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 la, la 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 la, la 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 la. Just tonight I stood before the pig barn, reflecting on the way things used to be. In the mud I saw a strange reflection. Was that hungry person really me? Those were long days, my friend, we thought they'd never end. We'd plow and toil forever and a day. We'd not the life we choose, we'd work and never snooze. Those were hard days, oh yes, those were hard days. La 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 la, la 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 la, la 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 la, la 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 la, la 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 la. Though some may yearn for simpler farmsteads, history shows this does not serve the poor. Technology has helped us feed more people, and now is not the time to shut that door. Those were long days, my friend, we thought they'd never end. We plow and toil forever and a day. It's not the life you choose, we work and never snooze. Those were hard days, oh yes, those were hard days. La 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 la, la 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 la, la 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 la, la 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 la, la 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 la.
So I'm going to be talking today about what role animal biotechnology is going to play in feeding the world. And When we hear that term, sometimes I think it's not sure exactly what it is we're talking about, and there's actually a definition of biotechnology, which is just the application of science and engineering to living organisms, and I think by that definition we've been doing biotechnology for a very long time, and I think everyone in this room is perhaps a biotechnologist. And as we look at the range of options that are up on the slide here, you can see technologies getting used in three main areas: genetics and breeding, nutrition, and health. And when we look down that list, there's some technologies there that are fairly uncontroversial. Artificial insemination, for example, used very widely, not a particularly controversial technology today. It was in the 40s, but not anymore. And then there are areas where I think there's probably universal agreement that you should, for example, try and vaccinate cattle to prevent them getting ill. You'll see there I've got some green colorings, and that's basically an estimation of the likelihood that particular technology is going to help with the basically animal production, particularly in the developing world, which is where I'm going to focus a lot of today's talk. And you'll notice, and this room will be happy to see, there's a large number of green boxes in the health area there, and I'm going to be speaking about that tomorrow in the Emerging Diseases Council session about where biotech is really going to be able to play a role in animal health. And you'll notice that there's really seen a couple of areas in nutrition and genetics and breeding where some of these technologies might have some benefit. And then you'll notice down the bottom there in the red, as in danger, don't go there, the technologies that are not seen as likely to have an impact at the current time. And I'm going to kind of have the second half of my talk focus on that because, as I think you'll see from my video, I'm pretty passionate about not stopping any technology from being available to producers, and that includes the more controversial topics of cloning and transgenesis. So I'm just going to pull from that video and talk about, for a couple of minutes, artificial insemination, which, as I said, is really a technology that has widespread adoption. And if you think about it, it's really quite phenomenal, the impact that a single animal can have as a result of basically semen freezing and artificial insemination. And pictured here is the bull elevation, who has about 6.5 million great-granddaughters in the US dairy population. And I don't need to probably tell this crowd the absolute importance that artificial insemination and inseminating the very best genetics in the dairy cow population has had on productive efficiency of the national herd. And what you see on this particular graph is the increase in milk yield per cow on average in the US. And right around 1940s is when you saw the introduction of artificial insemination, and you can see that precipitous increase as a result of the ability to use the very best genetics. And comparing 1944, milk production in the US were at about 53.1 billion kilograms versus 97 with less than half the cows, so down to 9.2 million cows from 25 million, we had milk production at about 82.2 billion kilograms. Now, I think that that has been a tremendous example of how you can improve production, but that's also been associated with the same socioeconomic effects that are associated when any technology gets adopted. That has undoubtedly changed the landscape for rural America. It's changed how many producers are involved in dairy farming, and it's had other consequences. There's risks and benefits associated with all technologies, and whenever we adopt technologies, there are going to be consequences of doing so. And this increase in productivity really has had a tremendous impact on the sustainability, if you will, or the carbon footprint per kilogram of milk. And this is basically, compared to 1944 values, the decreased levels of animal numbers, feed, water, land, manure and greenhouse gas per kilogram of milk, or per unit of outcome. And some of that has been a result of improved feeding. It's not only genetics, and also, of course, improved crop yields and the like. But if you think about the tremendous decrease in the resources that are needed to provide our dairy production, it's been quite an amazing story. And if you look at this particular impact in terms of production on the carbon footprint per kilogram of milk, it's really emphasised in this slide the importance of this, especially as we look across the world at the different productive capacities of different countries. So here we've got North America on the far left with the green bar showing us at about an average milk production of about 9,000 kilos. And the carbon footprint per kilogram of milk is the blue bar there. And as you see, there's an inverse correlation. As you have more and more productive animals per unit of animal, you have less carbon footprint per kilogram of milk. And that's particularly seen over in sub-Saharan Africa and Southern Asia, where we've got very low production levels in those animals and consequently a very high carbon footprint associated with a kilogram of milk. If we were looking at sustainability only from an environmental perspective, you might conclude that therefore we should all move to very high intensive, high productive milk production systems, and I'm not arguing for that because there's three components to sustainability. There's also the social and environmental aspects that have to be looked in there, and of course in Africa you're not always going to have a Holstein be very well genetically suited to that area, and so there is, I think, however, opportunities to actually increase yield a little bit that would have tremendous impact in terms of both feeding the people in those countries and decreasing the carbon footprint. And just to give you a feel, we've got an average of about 9,000 kilograms per cow, but the grand champion or the best yield ever was 32,800 kilograms, and so there's still a lot of productive capacity left, even in the Holsteins raised in North American situations. So if we look at the current status of the adoption of these animal biotechnologies in the more global sense of applying technology to improving animal production, there's a number of factors that influence their adoption, and I think you can kind of break them down based on whether they should be adopted in developing countries, should build upon existing conventional technologies. So it doesn't make a lot of sense to go suggest that a company or a country should start doing an artificial insemination program if they maybe don't even have any recording systems in place or no way to synchronize those animals. And so I think there's got to be some practical considerations of what technologies actually make sense in a country. They should be integrated with other relevant components of livestock production, and the application of biotechnology should complement other components of the production and marketing system in that particular country. And I think most importantly, you've got to make sure the biotechnology is going to be something that can be adopted, especially by people with maybe low technological skills, and not ram a biotechnology down the throat of producers, if you will. Make sure that it's actually something that suits their particular system. And if you look at the different columns that are in this chart, the one that, as I mentioned earlier, is seen as having the most likelihood of having impact in the developing world is artificial insemination, in part because it's not incredibly expensive to implement, and it can have very dramatic impacts in terms of improving the productivity of animals. That's quite distinct from the two down there on the bottom that have the dreaded red cross in the public and government acceptance column. And I want to turn my attention to that because it gets a little bit to the whole public acceptance of animal agriculture in general, and talk a little bit about genetically engineered animals. And for those of you that don't live and breathe this world, these are 5 very famous animals, and if you don't recognise Dolly down there on the left, she was the first cloned sheep, but the others are genetically engineered animals, and there's the genetically engineered chicken that was produced by the Roslin Institute that don't transmit bird flu from bird to bird. There's the omega-3 pig that was produced at the University of Missouri that's able to produce endogenous omega-3 fatty acids in its meat, and so you could have healthy bacon for breakfast, produced in 2006 at the University of Missouri. Mastitis-resistant cows produced by the ARS back in 2005. You'll notice a trend here, and that is all of the developers of these animals are not large multinational corporations. There isn't the Monsanto equivalent, if you will, producing these. These are publicly developed animals, and that actually is quite different from the seed industry and creates a problem when you have a prohibitively expensive regulatory framework associated with the approval of these products, because there isn't the large multinationals in the background to pay for those regulatory costs. And then finally, for those of you who haven't heard the story of the Aqua Advantage salmon, this is the Aqua Advantage salmon. The publication came out in 1992, but I want to make the point that this particular founder female, that is the transgenic fish that started the Aqua Advantage line, was created in 1989. That's a quarter of a century ago that the original founder fish was created. That's the fish that is where the growth hormone gene integrated into the genome of that Atlantic salmon. All of the subsequent generations have been bred the old-fashioned way, and that gene has been followed through just as you would follow through blue eyes or horned loci. And so I don't know if you guys remember the 80s. That was a long time ago. And, you know, I think that the hairstyles have maybe improved some. Certainly our computers have improved since then. Look at that cell phone. Wow, that's a honker. And then, I don't know, the computer games I actually think have gotten worse, in my humble opinion, but our cattle have certainly gotten a little shorter, because you can actually see the showers in the ring, as distinct from the 80s, where you had a hard time seeing whose cattle belonged to whom in the show rings. But 25 years ago, this is not exactly a new technology. What it is a fast-growing Atlantic salmon. It basically gets to 2 kilograms, which is about market weight, in 16 to 18 months instead of 30 months. Okay, so when this was developed by a university, by the way, not by a company, by a university, there was a thought that this would be a good thing to commercialize. And so this is the timeline of the Aqua Advantage regulatory process. So the original founder fish was created in 1989. And the FDA review of the salmon began in 1995. The first regulatory studies were submitted in 2001. Basically, there was about a decade of gathering the information, and to get a genetically engineered animal to market, it has to go through safety reviews. It has to be, the drug, because it's a new animal drug, has to be safe for the animal. The product, that is the flesh of the fish, has to be safe for the consumer, and it has to be safe for the environment. And so the company putting the fish up for regulatory approval has to provide the data to support all of that. The FDA VMAC meeting, Veterinary Medicine Advisory Committee meeting, reviewing all of the data, and what was proposed in this particular application was that these fish, these fast-growing Atlantic salmon, were going to be raised in contained on-land facilities in tanks. They were going to be all female and triploid, which basically is sterility in fish. And so it was going to be a contained on-land system for raising Atlantic salmon, is what was in this proposal. That was in 2010, and subsequent to that, there's been very extensive political efforts to try to stop the fish from coming to market. And as I stand here today in 2013, the company has spent over $60 million trying to get approval for a fast-growing Atlantic salmon. It still hasn't received regulatory approval. It's at the current time in the middle of a public comments period subsequent to the release of the environmental assessment. And basically, this has had a very inhibitory effect on anyone's interest in investing in this technology, and I don't know a company that could cope with that sort of regulatory uncertainty or cost to bring a product to market. And consequently, GE animals for food are moving to other countries with less prohibitive regulatory paradigms. In 1985, this was kind of the landscape in terms of research labs that were working in genetic engineering. And 20 years later, in 2012, you'll see there's been a migration, if you will. There's been a migration where people are now working in this, particularly in China, whose government is investing a lot of money in developing genetically engineered plants and animals, and also South America has started to adopt that technology. And perhaps that's rightly so, because that's where a lot of the hunger needs are, and so that's a good place for that technology to go, I think. But I just want to kind of talk about the fact that we have this very, very, very expensive regulatory process. And my basic question as a scientist is this. You know, the first genetically engineered crop came to the market in 1986. Last year, 17.3 million farmers planted GE crops. They made the choice to plant GE crops, and they were grown on over 170 million hectares, and of these, about 90% were small resource poor farmers in developing countries. So this technology is being adopted in the developing world. We and our livestock have consumed billions of meals, and there hasn't been one documented case attributable to the GE nature of the materials consumed causing safety or health hazards. The current products of GE are singled out to go through a very expensive and lengthy regulatory process, and that adds years and millions of dollars to the bringing to market of each genetically engineered crop transgene combination. And as a scientist, my question is this level of scrutiny really aligned to the science-based risks that are associated with this technology? What is it showing after 20 years of safe use? Or is this overabundance of precaution really making the development of this technology beyond the means of all but the largest multinational corporations to the detriment of global food supply globally? And I don't argue that we shouldn't do a safety evaluation of new novel traits, and especially if we're bringing in a protein that hasn't been eaten before, we should absolutely do a toxicity and an allergenicity test, whether they're brought in by GE or conventional breeding techniques. I don't care how you made it, it's the product that should be regulated, not how you made it. But a lot of the safety testing is involved with these unintended or unanticipated or unknown magical side effects that we're looking for, and it's really this testing that really puts you on shaky ground scientifically, because what's the appropriate sample size to test for an unknown, and what level of change would be detrimental to public health? If you don't know what it is you're testing for, you can't set up the appropriate sample-sized experiments. And basically, when we started this 20 years ago, we had very little empirical data about the safety of these crops. We've now had hundreds of regulatory approvals and spent millions and millions and millions of dollars showing that basically the composition of transgenic crops is the same as regular crops, except for the one protein that you're expressing. We haven't had any unanticipated consequences of this technology. We've had a 20-year experience now to where it's becoming more dubious to continue this ever-increasing regulatory burden on a technology that's not shown to be any different to conventional breeding. And it seems more scientifically defensible to me to say, yes, let's look at the toxicity of the product, let's make sure it's not an allergen, let's make sure we didn't have insertion effects or we didn't go into a gene. But it just seems a bit strange to me that I don't really know what it was I was looking for, but I'm relieved to see it wasn't there nonetheless. As a scientist, that just isn't a very comfortable position to be in. And, you know, skeptics will say, well, you know, that the absence of evidence is not the same thing as the evidence of absence. And while I don't disagree with that, and I'm not saying that the risks are absent, I think, or at least have proved that they're not absent, but you can't prove something is absent. That's really logically impossible. And if you look for something for 15 years and fail to find it, then surely that must be accepted as evidence of absence. And I think that, you know, how can we spend $60 million getting a fast-growing fish to market when if I, as a conventional breeder, I can breed fast-growing salmon the old-fashioned way and bring it to market? It's got exactly the same phenotype and environmental concerns associated with it as the genetically engineered fish in terms of it's a fast-growing salmon. That's all it is a fast-growing salmon. It's got the same risks associated with it, but I would have absolutely no regulatory oversight using conventional breeding techniques or radiation mutagenesis for that matter. And I found it's not often I laugh when I read scientific papers because they're really the most dry, boring form of communication I think humans have ever developed. But I was reading this particular paper about GMO biosafety research in China, and I love this quote. And basically the gentleman said that historically the risks to the environment presented by crop plants are low, and he went on to explain their regulatory approach to looking at the risks associated with genetically engineered crops, and I just love this. We are not trying to prove how risky it may be by some strange imagination or by inventing some special phenomena that do not occur in nature. And I totally agree with that, and I feel that that's what we're doing to genetically engineered organisms. And, you know, the GE burdens are not justified by the scientific evidence or our 20 years of experience. And whilst we do need to have regulations in place on new technologies, in a world with the demand that we're going to have to feed those guys, I just don't think we can have this absolutely precautionary, prohibitively expensive, time-consuming, uncertain regulatory approach for genetically engineered plants and animals. And I think the trigger for regulatory review should be the novelty of the trait, not how it was made. And the severity of the control should be directly related to the actual relative risks associated with the novel characteristic or phenotype. I can't tell you how many times I've had discussions with people about the GE salmon where they're worried about Atlantic salmon interbreeding with the Pacific salmon off the Pacific. And it's like they don't interbreed, and if you're worried about that, conventional salmon farming should be equally of concern to you where they've got Atlantic salmon in sea pens. And so we're not comparing the risks to current production systems, we're comparing it to zero. And, you know, everything's involved with risk, and if we only look at the risks without also looking at the benefits, then I think no technology can ever come to fruition or market. And we do a cost-benefit evaluation every time we do anything in life. Why would we not do a cost-benefit evaluation of this particular technology? And so I think, you know, when we're looking at GE, there are things that we can do with new biotechnologies, gene editing technologies, that are going to give us the ability to do some amazing things. We're going to be able to go in and selectively make polled Holstein cattle quite easily. It won't even leave a genetic footprint. I think we should. We're going to have the ability to go in and gene edit certain genes to alter their disease resistance, to alter their growth characteristics. I'm going to talk tomorrow about disease resistance. Can we make all our chickens and dairy cows female? I think that's going to be an animal health benefit. And I'm going to just finish up with this couple of quotes here from Mark Linus, who was formerly one of the most strident opponents of GE crops and food, who basically had a change of heart at the Oxford Farming Conference earlier this year, and basically came out and said, I think, what a lot of scientists have been thinking, but maybe not willing to say out in a public setting, and that is that the movement against this technology has really hurt people and it has contributed to food insecurity, and this continued precaution is going to do so. And I just want to finish with, it's basically beautifully followed on from the previous talk, which has to do with the hunger map of the world, and you'll notice particularly Africa is the darkest area of all there. And I want to now superimpose on that where genetically engineered crops have been allowed to develop in this world. And basically the green is countries that allow the planting of biotech crops, and the yellow is where you're allowing the importation of biotech crops. And there's almost an inverse relationship between the most food insecure areas and the ability to use this technology. And you'll notice that China and India there have adopted it, but so far in Africa there's only 2 countries that have given the ability, or have been given permission to grow GMO crops. That's South Africa and Burkina Faso, and basically that's because they have all implemented this very precautionary approach to GE crops, basically inherited from the EU's precautionary approach, and really we're not allowing that technology to help with the food insecurity in those nations. And I'll finish with a quote from a gentleman that's no stranger to this audience, Norman Borlaug, who I think just sums up beautifully the challenge we face in terms of allowing technology to get used by developing nations and not putting onerous regulations on a technology that really could help to feed people.